Math and Beats. In this video, we are going to focus on the topic of what is called critical points, as these critical points, as we'll see, do play a significant role in determining local extrema. Yeah, let's go. All right, so what's the definition of a critical point? Well, first of all, for every critical point, we assume we have this number c that is in the domain of a function f. So we got to first assume that the function is defined at this location of c. Given that, then we say that this value x is equal to c is a critical point, and in this case we classify it as a type 1 critical point if the derivative at this location c is equal to 0. Sometimes, by the way, we can replace critical point with the word critical number. So sometimes those two phrases are used synonymously. So if you have a value of the input, which is in the domain of the function, and the derivative at that same value, in this case c, is equal to 0, then we call it a critical point of type 1. But there's another type of critical point right here at the bottom. We say that x is equal to c is a critical point, or a critical number, if you will, of type 2 now, if the function's derivative at this location c is now undefined. So both of these cases, we need the function to be defined at the location of c, and you either have a critical point of type 1 if the derivative at this location is 0, and you have a critical point of type 2 if the derivative at this location is undefined. That's how we define them. Let's take a look at some various situations involving critical points. So in particular, we're going to look at some graphs involving critical points here to try to see why it may be useful in looking at local extrema. So here is one such situation in which we are given in this picture the graph of the function f of x, and here's this location c, and notice that if I go and I draw a tangent line at this location c comma f of c, the derivative there is going to be 0. So right here we can see that f prime of c is equal to 0, and moreover c is in the domain of the function f here, and thus x equals c is a critical point, and in this case of type 1, because the derivative is 0 at this location, and we have also that, of course, the function is defined at this location. Notice that in this particular example, we do indeed have a local extreme point, a local max, at this location c comma f of c. So there's one such example. But we're going to look at a few more here before we try some other things. Here's another situation. Here's a function. Again, y is f of x. And again, we have this location x is equal to c, which is at this corner point right there, right? And so because there's this corner at the location of c comma f of c, then in this case, the derivative won't be defined. So in this case, f prime of c is undefined. And again, taking note that c is in the domain of the function, and therefore by definition of how we're classifying these things, the location of x is equal to c is a critical point, in this case, of type 2. And again, in this example, we have a local max point at x is equal to c, a local extreme point. Just keeping it in mind. Look at a couple more here. Here is one in which we have a discontinuity happening at x is equal to c. So first thing to note, c does belong to the domain of the function here, right? It is defined. There's the value right there, whatever that output value happens to be. So it is in the domain. However, because we're discontinuous at x is equal to c, it follows that f prime of c is undefined. And in this case, we would say that x is equal to c is a critical point of type 2, because we have the derivative is undefined and the value of x is equal to c is in the domain of the function. Notice that in this case, if we use the definition of a local extreme point, in this case a local min, if I draw a little arbitrary open interval around x is equal to c, and I go up to my values of the function in this arbitrary interval, we can see that all values of the function right up here in this open interval are bigger than or equal to the output value of f at c. And in this case, we actually have a local minimum point in this situation. So first three examples, a variety of different things happening, and in each of those cases we had a local extreme point. And the question is that always going to happen? Well, let's see. Here's another example. Here's a function, kind of looks like a cubic function here. And again, we can take note that c is in the domain of the function. And if you drew a tangent line at the location c comma f of c, draw a little line there, straight as it can be, we notice that f prime of c is equal to 0 there, right? But, however, we don't have a local extreme point. But before we get into that, take note that we still have a critical point at c comma f of c. So in this case, x is equal to c is a critical point of type 1 in this situation, because we have that the value of x is equal to c is in the domain of the function and the derivative there is equal to 0. We do not have a extreme point here though, however, right? Because if I move to the left of c and I move to the right of c, there are values that are both bigger than this output of f at c and also less than that. So here's an example in which we have a critical point, but there is no local extreme point. Okay, one more here. Okay, here is another function, y is f of x, and kind of looks like maybe a cubic function of some sort. Notice that the function does have an output here at x is equal to c. So again, c is in the domain of the function to begin with, which we need. And notice that if I try to draw a tangent line there, my tangent line is going to be a vertical tangent line. And for that reason, f prime of c is undefined, and moreover, we get that x is equal to c is a critical point of, in this case, type 2, right? Because we have an undefined derivative where the c is in the domain. And notice that at this location, c comma f of c, we do not have a local extreme point again. So we start thinking, okay, what's up with these critical points? Why do we care about them? Well, we can see through the variety of graphs we just looked at that just because we have a critical point doesn't necessarily mean that we have a local extreme point. However, in all the cases that we had a local extreme point, we always had that location was a critical point. And in fact, this leads us to a theorem, and that is, if a function f of x has a local extreme point at the location of x is equal to c. So we're saying we know there's a local extreme point there. Then what must be true? Well, then that location x is equal to c must be a critical point of the function f. However, the converse is not true, right? As we saw, if you have a critical point, you don't necessarily have an extreme point. However, if you have a critical point, you might have an extreme point. And in fact, the only locations for which a local extreme point can exist are going to be at these locations for which we have critical points. Now, we're not going to prove that theorem right here in this video, but hopefully the graphs from the prior examples help justify that this is true. Let's take a look at a couple last examples here to wrap up this video, in which we're not given graphs, but rather we're given actual functions. So we want to, in each of the following examples, find and classify all critical points, meaning type 1 or type 2, for each of the following functions. First example here, we have a polynomial function, f of x. Now we know polynomial functions are defined for all real numbers, and they're also smooth for all real numbers. So we should expect that if this function has any critical points, then they would be of type 1. Let's see. Well, the first thing we have to do, of course, is find the derivative here. F prime of x is going to be with just a bunch of power rules, so we're going to get a 6x squared minus an 18x plus a 12. And notice that this is the same as a 6 times an x squared minus a 3x plus a 2. And furthermore, we can factor this to 6 times x minus 2 times an x minus a 1. Now, we can see that the derivative is never undefined. However, it does equal 0 if x is equal to 2 and x is equal to 1. And thus, both of these values right here, these locations, both are critical points of type 1 because the function is defined at these locations, and moreover, the derivative is equal to 0 at these locations. Let's do one more. Here's one. This function g of x is 4 times x to the 3/5 power minus x to the 8/5 power. So we have two different terms in this function that have fifth roots involved. And we know that roots that have odd indices, right, cube roots, fifth roots, 7 roots, etc., those are going to be defined for all real numbers x. So we should take note that the domain of this function is all real numbers x, and so any type of critical points that we're looking for, we know that already these values are going to belong to the domain of the function. Now, what else happens? We need g prime of x, so let's apply our power rules. We get a 4 times 3/5 times x to the negative 2/5 there for that first term, minus an 8/5 times x to the 3/5 power. Now let's clean this up a bit because, again, we need to figure out if this derivative ever equals 0 and also if this derivative is ever undefined. Notice for both of these terms, I can factor out a common factor, and that common factor being a 4/5 from both of the terms, but also an x to the negative 2/5 from both of the terms. What's left over? From the first term, there will be a 3, clearly, and then what power of x times x to the negative 2/5 gives x to the negative 2/5? Well, it's just 1, right? So just left with a 3, and then minus a 2. 4/5 times 2 is 8/5. And here we would have to have an x attached to this, since x to the 1 power times x to the negative 2/5 power is x to the 5/5 minus 2/5, giving me 3/5. So there's my factorization for this derivative. And of course, if I rewrite it just one more time, this is the same as 4 times 3 minus 2x divided by 5 times the 5th root of x squared. Just putting that term in the front in radical form and in the denominator with a positive exponent. So you think, okay, what value makes this 0? Is there any? Well, yeah, there is. G prime of x is 0 if 3 minus 2x is equal to 0. And of course, if you solve that, you get x is equal to 3/2. Is g prime of x ever undefined? Well, yeah, it is undefined if x is equal to 0, right? If x is 0. Why is that? Because if I plug in 0 into that derivative, well, I'm dividing by 0, and hence the derivative is undefined. But take note, x is 0 is part of the domain of the function g, and x is equal to 3/2 or 1.5 is also part of the domain of the function g. So both of these are critical points, but they're different types, right? X is 3/2 is a type 1 critical point because that's a location for which the derivative is 0 and the function itself is defined. And x is equal to 0 is also a critical point, but it's a type 2 critical point because the derivative is undefined, but yet the function is defined there. So we didn't say whether or not any of these critical points we found in these last two examples happen to also give us extreme points or not, that is, local extreme points. However, that is something we are going to get into in a future video. This video was more focused on what are critical points, what might they tell us, can we identify them graphically, and can we identify them through algebraic methods, using some calculus as well, of course. And that's it for the video. We're going to continue focusing on extreme points, both local extreme points and global extreme points, in the upcoming videos until we can get an overall strategy for finding and classifying all the different extreme points for a function. And until then, you know it, it's Math and Beats, and I'm out.